cases, you have different average surprise that you can measure out of this formula. And for more the choices in a system, the more surprise that you might expect, as you can predict. If you have 5 choices, any 5 equally likely outcomes, the surprise of any one of them will be a very big surprise for you. Okay. So this is a more technical way to think of surprise, which is how many information that you can transmit of the overall system. So this is the code paradigm is a computer science paradigm, but formally you can think of it because of historical reason. It is named as like information entropy, and entropy usually derived from like how many bits you can send to actually describe the whole system. But for now, you can think of it like surprises. Okay. So shorter codes for common events. Similarly, the surprise will be less for common events. And okay, so another way to kind of interpret the surprise is no matter how clever you send the information, the averaged code length for surprise can never go below the what we have discussed. So can never go below this formula. So now here we enter the fundamental problem, which is the model that we have is actually different from the true distribution. So what we have discussed is the surprise that we have just formulated is measured based on the true distribution that we have known. So go back to this part. So we have the surprise in here measured in log of probability, and this term is actually refers to the actual true distribution. So we are averaging our surprises. The problem is we only will see the data that we have is this distribution here, but what we don't know is whether our model is correct or not. So this term will be our model, and our model may not be correct. So that's why we have another term called Q here. The Q refers to the code book, or the model, and the data that we have follows the true distribution of P. And therefore, we can measure how far that we want to have that we want our model to be not different, to be the same as the true probability distribution. Okay, so go back to here. The code is an assignment of binary string. It is sequence of 0 and 1 to each possible outcomes, and every time an outcome occurs, you transmit this binary string. So for say this system, if it is sunny, you say 1, 0, and if it is cloudy, you transmit 1, 0, and if it's rain, you transmit 1, 1. So each morning, if you transmit one binary string, on a Sunday, you transmit 0, and on a rainy day, this is the code length of how many bits that you need to transmit for that event. And native codebook for the same length for every bit will cost you 2 bits actually per forecast. If you are being smart, you can reduce this to 1 bit because this is fairly common. And for cloudy, you only send 2 bits. So on average, you can send less bit over the communication of events. And this concept highlights to the concept of surprises. So for the certain events, the events that with zero surprise, you want to represent the outcome using as fewer bits as possible. So by matching the length, the code length to probability, and the smart codebook saves 0.5 bits per forecast, and it matches the surprise exactly. So the way we measure surprise ties back to the efficiency of transmitting the information across. So the entropy is the minimum price of communication, and these are the actual computations. So you put the probability of each event and compute the surprise and sum them all up together, and you will arrive 1.7 bits, which is the information cost that you need to transfer the weather in a long term, in a sequence of events. Okay. So, but the problem is the P is hidden. So we compute the surprise using the probability distribution of P in here. But the problem is we will never know the true distribution of the events. So you cannot, you can sample it, but you cannot actually directly get the true distribution from the real world. So the best way to do it is to estimate with your model. So the model learns from the data, and all you have to do is work with the model and update the model. So the question now is you have your model Q, and you must build the codebook using Q without having the true P distributions. And by through this learning process, the information that you have lost will suffer from the inaccuracy of your model. So the price of an inaccurate model can be measured by the differences between the probability distribution of the true distribution and your model probability distribution. So this is what the cost of the incorrect parts of your model. So from this slide, you can already predict we can actually use this information to correct our model. And in here we have, I think the model incorrectly predicts the weather of sunny is 70%, which actually is 50%. So it costs 0.5 bits and 2.3 bits, and so on and so on for other cases. So we can kind of rethink of this problem as paying the Q prices at the true weather rate. So the average cost of how often events happens multiplied by the price of the model assigned to it, and sum over all the events. And this is the price that we are going to suffer from. So this is the true distribution of the event and how often it happens, because that will mean how often you will get it wrong, and the price that you have to pay. And so this is the expected price of the actual code. So in this example, we have wasted around 0.165 bits, which refers to the model error. So of this example, we just compute the cross entropy of P using the model Q. And the optimal price that we have to pay is 1.5. So the gap of 0.1 bits is pure. So we actually want to eliminate that part of the waste. So as I mentioned, in the real world, we do not know the true distributions, and we use approximate model Q. And cross entropy actually measures the surprise we are on average when the events follows P, but now we use Q surprise value. So the cause of being wrong is essentially the cross entropy. So summing up all the probability or all the data set with our inferences of the model, and we can measure the cross entropy. And we backpropagate this kind of information to a neural network to update the actual model. Okay. And using, so this term is the cross entropy formula, and there is another way to write it down so that we can do some mathematical trick on this formula. So P is, we will rewrite the expectation of sum over all the probabilities to an expectation. So instead of actually compute all the possible cases, we will be actually doing sampling. So this kind of trick refers to the multi-cause simulation, where all we need to do is use our model and sample the real-world data. Okay, so this term is just rewriting the part that we have discussed into the number of samples that we have to kind of approximate the true probability distribution. Because this formula says that we have to sum over across all the possible outcomes, which is, I think, impossible for the image cases. Therefore, we will suggest maybe we will just sum over our data set, so in order to correct our model. So cross entropy loss in every neural network is exactly this estimating, and training on a mini batch is similar to one multi-cause step. So we have discussed this, and we have in the case of cross entropy introduced both inherent uncertainty of P and the extra cost of using the wrong model. So this part is irreducible, and this part is the model error. So the error between the actual distribution and the model that we have. So KL divergence strips away the true reducible error to isolate the pure cause of Q being different from P. Okay, so these are some derivation you can look into. is simply simple math manipulations of taking the sum, combining two sums together. And we have this as our KL divergence formula to measure how wrong our model compares to the true distributions. And this form allows us to actually sample from our sampling from our data. So this is the numerical way to compute the KL divergence of this sample. And these are some properties of KL divergence. And there are different ways of actually, there are different mechanisms of measuring KL divergence in different machine learning tasks. So I think I will go over this when we arrive at when we are using KL divergence. For today, we will be using KL divergence in diffusion. So we will try to understand the diffusion process using KL divergence. In the diffusion process, it introduced some key parameters such as the time steps and also some guidance, which is not shown in here. But the essential part of diffusion is the time step. So we will talk about how the time step was introduced in this loss function, and we will try to have a glimpse of what the diffusion process is. And after understanding the diffusion process, you might have kind of basic understanding of how the voice is actually being simulated. So do not worry if you do not quite understand it up to now. We will go back to these slides again and again, like the aura that we did, because it's quite the essence of machine learning. Okay, so these are the recap from last semester. Now we are going to talk about audio as number. So as you might recall, sound is a pressure over time. So when you speak, your vocal cords actually vibrate and push air molecules to create a pressure wave that microphone samples as voltage, I think around 16K times per second. And the Nyquist theorem requires sampling at least twice as the highest frequency of interest. So human speech tops out near 8 kilohertz, so making sampling 16 kilohertz depending on waveform. So 1 second of speech will produce 16K of numbers, and 3 seconds of recordings is around 38K. So why do we not use raw waveforms as the input of neural networks? It is because two waveforms that is identical to a human can have completely different numerical values if one uses time shifted by a few milliseconds. So neural networks need features that are locally invariant and meaningful, which is why we use short time Fourier transform that provides it. So just for recap, short time Fourier transform slice the waveforms to overlapping 25 millisecond windows and apply Fourier transform to each of them. And producing a frequency by time matrix and or a spectrogram, which you can see here. The x-axis is time and the y-axis is frequency. And Whisper, the model that transcribed uses Fourier transform of 400. So say 25 milliseconds and 16 hertz with a hop length of 160. So 1 second of audio produce 100 spectrogram frames. And the output is a complex matrix, which takes magnitude of square to get the power and give a real-time frequency times time representations. Okay. So we will scale, we will use the mouse scale to match the human perceptions. Essentially, because human hearing is logarithmic, and we perceive the differences between only 100 Hz to 200 Hz as the same intervals as 1000 Hz and 2000 Hz. So we pass through these Bell filter bands, which applies 80 triangular filters based on the mile scale, essentially the log scale. So essentially, we pass the filters of human speech into this filter in the frequency space. So you can think of you multiply by this graph. You just simply multiply by this graph and then with this one, and then the filtering already can apply because but you have to kind of rotate this graph and multiply. And taking the log base of 10 is logarithmic that they use. So after the filtering and log compression, 1 second of audio becomes 80 times 100 matrix, and 80 by 100 time frames. So Whisper Pet was trained all the inputs to exactly 30 seconds. So it will seize 80 times 3000 regardless of the actual audio length. And this fixed shapes is what enters Whisper encoder and what the text to speech encoder learns to write. Okay, and there is other technique for processing audio. So it's called RBQ, discrete tokens for audios. Very similar to the code book that we introduced just then. So the reduced vector quantization compress a waveform into a sequence discrete integer tokens by repeatedly quantizing the residual error with the learned code codes. So a 24 gigahertz waveform will be around 24 flows per second, becomes roughly 150 RBQ tokens per group per second. So the process looks something like this. You have the input vector and you compare with the code book, and you find the best match of the code and output the token. After this, you subtract the residue. So with the code book, you have the waveform, and you subtract with the original waveform, and you have residue too. And you also pass through the code book and find, we have another token match. And you repeat this process over and over again, so you get a list of tokens. So continuous feature vectors is compared against the code book as I mentioned, and the codebook is a learned dictionary representative vectors, and the integer index becomes a compressed representation, and the vector is quantized, replacing it with a high-dimensional vectors, very similar to what we did in the text and the image as well. So the compression that RQV did is quite extraordinary. So after compression is around 160 times smaller than the original token. So we compressed the raw audio of 1 second and compress and transform the audio to our BQ tokens for 1 second, which means this compression is essentially indistinguishable to human ears, enable the language model to generate audio as a token sequence. Okay, so we have just discussed about how the audio is transformed into these sorts of tokens and these sorts of numbers. So we have this space, which is frequency by time, and also we have another method called tokenizations. Okay, so there are two ways that we can reformulate a waveform function as a matrix. Okay, so I think you have already learned about what Whisper is in the last semester. So the Whisper architecture is essentially using the waveform from the log mile spectrogram, 80 times 30, 80 by 3K matrices feeds into the encoder with convolutional neural network, self-attention, and also fully connected neural networks. And it will pass on to the decoder with a masked self-attention and cross-attention as well. So we've talked about cross-attention and masked self-attention, then it is very simple way to kind of merge two different kinds of data modalities, and the output would be text. So the encoder pipeline that we have discussed use all these kind of network self-attentions and fully connected with an activation function and output a dimension of 1,500 by 1,280 dimensions. So the decoder pipeline looks very similar. So the encoder input will be input to the cross attention with the previous token and the positional embedding input to the mask attention and then cross attention, and then it can generate text with, of course, you can sample it from either using deep search or greedy search. Similar to the Peligamma that we have talked about, it also uses specialized token like start of transcript token, language token, and then task token, which do I need to transcribe or translate, and also timestamp tokens and the output of the transcript. So Whisper Large is it have around 1.5 billion parameters, 32 encoder layers, 32 decoder layers, and window size of 30 seconds, and the dimension it used is 1,280. But lab that we're going to do use actually a different whisper. It's called faster whisper. It uses the technology of C translate, and essentially the faster whisper have identical performance. The performance is measured by word error rate. Word error rate can be calculated with this formula measuring the quality of the transcript. And faster whisper uses CT translate, essentially a C++ library. Fortunately, with vibe coding, I think it is not a problem to write in any language anymore. So fast whisper use C++, which is faster than PyTorch. And also use less VRAM and 4 to 5 times faster, and the performance is essentially identical. In the code that is given to you, the compute type is flow 16 with a beam size of 5. I presume you can recall what a beam size is. Essentially, when you do any auto-regression task, you need to do sampling. So sampling can be either greedy or using temperature or using other different ways of sampling. And beam search is users who look into look into a certain number of the next type token and compute the optimal sequence. So when beam size set at 5, you will look into the next 5 tokens and compute the optimal probability. Okay, so we think about this. Okay, so on top of the fast whisper, of course, use the CT2 engine. It can do batch recording and KV cache reuse, and also in place optimization. So all of these features allows the faster whisper to be faster than whisper. Okay, and it also have word level timestamp. So in the code step, say the token generate the token hello, and uses cross attention, and then from here it will learn about the attention weight distributions and generate encoded frames. So this is time. So you will see where the time is actually is. And the voice detection also fast whisper. You can also couple with other kind of voice detection, voice activity detection mechanism. So before whisper, so you can use a model, voice detection model called silly road, and to detect the speech only, trim out the segments and give the whisper to transcribe. Okay. So fast whisper leveraged this technique and to isolate the part that only contains speech, so it will not waste time on the other parts without speech. So that's one other reason that faster whisper is even faster. So detecting the voice is fairly simple. It's just use a CNN and LSTM, and then to detect speech. Okay, so from the lab, this is the actual configuration of the code. So Whisper control the text to speech, speech to text progress, and here are the configuration. So in the project, I presume if you pick this one as your project, you might want to tune this parameter. Say for example, setting the beam size to higher will give better results. Because I often heard of users of whisper comment that, oh, it is very bad and the results is not good. But they have overlooked into the details of the configurations. So I think this is quite important, because if you set the beam size to a larger value, the performance is actually pretty significant, I would say. And if you also add the filtering, it also will perform much better for the transfer. Okay, so these kind of configuration are for your project to investigate. And the output files in the lab is whisper transfer. So in the project, maybe you can find a very difficult audio for you to transfer, and try to tune different parameters and see if the word error rate improves. Okay. So of course, in your project you can fine-tune whisper if you want. So it is one of the project ideas that you load whisper in 4 bits and inject the LoRa adapters and train for 3 steps, and then save the word error rate and see if you can have some improvement. So this is one of the project ideas that you can make. And you can comment on the fine-tuning properties and why you use quantized LoRa. Okay, so you can actually incorporate this into your project. And of course, in your project, the mark will be measured of what you have tried, and also the mark will be marked against what you have reasoned about. So it's not really about the actual performance, or whether that you can actually fine-tune the model or not. So you can say, for example, 4-bit quantization and LoRa adapters that you have used. And the way that you try different kinds of configurations of LoRa. And of course, this is the LoRa model. Okay. And you can try different target models in the attention. And of course, you can try different configuration and see if you can improve the word error rate. Okay. So the output files should look like this. So this is actually an example of the project. So these sections are some of the examples of what you can do. Therefore, it is not in the code that I have put up in the model. But if you follow these slides, I think you can do a pretty decent project. Okay. So we have talked about how machine hears and writes it down. Now I will talk about how machine actually generates voice. So previously, there are some different attempts to generate voices. And why it is more difficult than transcription, because it is a generative task, which generation need to map one text into many possible audio, many possible valid audio signal. That is a one-to-many situations. requires that the model can sample from the distributions. So as you can see why it is difficult, because if you think about model classification, image classification versus image generation. Image generation is a significantly more difficult task than the image generation. This is same as the voice. So transcription is much easier, but generating a voice is much harder. So early text-to-speech architectures like Tetron produce early over-smoothed mild spectrogram because the means were error rates training average over all valid realization rather than sampling from them. And every generative model family in this section, including variational autoencoder, GAN, and normalized flows and diffusion, and flow matching exists to solve this blurriness problem in a different way. And we are just going to talk about diffusion in this section. So go back to our lessons on how we interpret the model. Of course, the generative part, the generative idea takes on the Bayesian approach. So if you take on the Bayesian approach, which means is to sample out of all the possible valid voice signals, and you try to sample the one part that the model behaves naturally. This is the diffusion process that we're going to talk about. Okay, so we spend much of the time talking about the KL divergence, and these models use KL divergence to actually do the generative task. So there are multiple ways to do it, and of course, diffusion to be one of the most promising one, and also the one that we're going to try in our lab. And I think most recent success diffusion model is called the denoising diffusion model. This denoising diffusion probabilistic models, which gradually adds Gaussian noise to a data over t time steps and train a neural network to reverse the process and generate samples by iterative denoising starting from pure noises. Okay. So the model that we are going to test on uses flow matching. So flow matching learns a continuous time vector field that maps the Gaussian distribution to the data distribution in a straight line path, and converging faster than the denoising diffusion probabilistic model, and requiring fewer functions, function evaluation, and the inferences. So Garoku is the model that is used in the lab. So Garoku is a very small model. Only it's not even in a billion size. It is only 28 million parameters. Flow matching text-to-speech generation model on a multi-speaker data set. Okay. And it is Apache licensed. So this is the Garoku 82 million architecture. The input is text, and it will use a BERT model as the text encoder, transform the text into embeddings. and uses style, uses diffusion to work on the style, and finally decode it back to the voice. So in the text encoding layer, it uses raw text and pass into genomic bird and output text embedding. So text into it and convert to the text encoding. And then it will pass into the diffusion model, which it is a denoiser diffusion model, and sample the style vector of S. So, and then after we have the denoiser vector, we have the style with the embeddings, and we will try to upsample it with an injection. So the style decoder is a method used in here is ADA injection. So it's a method used in adaptive instance normalization to copy style like speaker voice, tone, or singing styles from an audio samples and apply to another. So it works by first removing the original style from the middle features of the model by normalizing them and subtract from the mean by their standard mean deviation per channel, and add the new style and average the variations. So from the vocal folder, it will transform, it will feed into the mouse spectrogram into a special type of network, which is kind of a smart neural network, which turns the mouse spectrogram back to very audio, very quickly. So it's kind of using a inverse short time Fourier transform to do this, but it does this in a new neural network way. So in summary, that's how in general how the machines speak. So I've introduced multiple models in this section. It's called GAN, or of course diffusion, and these sorts of models produce different types of different families of text to speech generations. All of this work. So if you're working on how to generate speech in this course, and you might need to try different ways to kind of generate different voice to kind of evaluate whether it is good or not. Because a generative task normally is a much difficult task than speech to text. So in order to evaluate across different methods, the only thing that you can do is to try them and compare their performance. So voice cloning and voice conversion are two different programs. So what I want you to take back home is that you might need to think about, if you want to do voice generation, you might need to think about what models that you are going to pick and the mechanism behind the models. Okay. I think we only have time for voice cloning for this lab. And voice cloning is different from voice conversion. So if you record a voice and you try to convert it into yours, it is called voice conversion. For voice cloning, it is a text-to-speech based method. So I record say 10 seconds of your voice, and I will try to make you say anything that I want. So it's a text-based, text-to-speech based model. So the input is text and the output is speech. in the target voice extracted from a short reference clip. Okay. So here is a quick overview of how zero-shot voice cloning works. So, of course, a speaker encoder, typically a fine-tuned model, will encode your voice and output a dimensional embedding vector which captures the speaker timbre without any text alignment. So it will only capture the timbre of the speaker. Then a text-to-speech model generates the residual vector quantized code token sequence will conditionally join on the theorem of sequence from the text input and the speaker's embeddings. And with the decoder, the decoder will try to decode all the vectors back into a speech. So converts the token sequence back into a waveform carrying the target speaker voice characteristics. And the residual vector will extract content features from the source audio using a neural network wave LM derived by the Hilbert model that strips speaker identity, leaving only the phonomic content as the frame level embedding sequence. So this is voice conversion in overview, and it then retrieves the nearest neighbor of frame from a fast index and build the target speaker's training audio and replace the source content embeddings with the target speaker embeddings. So essentially, to make it short, retrieval-based voice conversion is essentially playing with different kinds of embeddings. So extract the content features of the source audio using Hilbert model, strip the identity out, and inject the source content embeddings with the target speaker embeddings, and to match the phonomic positions. Okay, so in order to protect your voice, spectral or detect whether it is cloned or not, spectral detectors is looking for clip code artifacts and the quantized vectors, residual vectors boundaries, so which is a natural, smooth, or redundant. So these are some defense mechanisms that you might want to talk about in the project. But of course, in the project, you can skip this part if there is not enough time. Today's lab, we will be only using, we will be only introducing voice cloning. So clone your voice for 10 seconds, no fine-tuning required. So the model used in the lab is called Chatterbox. It is only 500 million parameters with zero shot that can generate a list of language. So if you record yourself, say in English, you can translate it into English, French, or Chinese. So with the reference audio, it will use a special tokenizer, transform the waveform into into the speaker tokens, and then it will take in a target text and also a text tokenizer, and this one it will merge them all into a Llama 3 backbone model. So it will convert the speaker tokens to text and to speech tokens. Finally, it will use the GAN vocal decoder to decode back into the waveform. So the 3S tokenizer converts a reference waveform into discrete speakers prompt tokens at 25 Hz and captures the identity, timbre, and speaking style. And the reference waveform, so this is the reference waveform, converts into the spectrogram, and also will pass into the sense voice, a large decoder, and then will produce the Coco discrete tokens at 25 Hz. So eventually it will be tokenized. So the S3 tokenizer will train to maximize the schematics and speaker discriminality. So not the audio reconstructions like the residuals, vectors, Coco. And the causal semantic content, what's being said, and speaker's identity, who sends it, and also the language, the paralanguage clues, such as their emotion and speaking rate. And then after that, the model will put the speaker prompt, the tokens, and also the tags, and ask it to generate. So the causal language model receives a combination of token sequence and auto-regressively generate the speech tokens using the Llama 3 auto-regressive decoding method and predict the speech tokens. So with the speech token, the harmonic noise source filter, it will ultimately decode it back into the waveform using the inverse Fourier transform decoder from the marker. So there are different vocal coder for you to pick from, and these are the things that you can write into your report, saying for what reason that I will write that I use this kind of model. As long as you kind of reason every choices, that's fine. So there is no right or wrong of which model that you should be using. So finally, it will be watermarked. So every output carry and watermark. So surviving the MP3 or resampling on page. So it's essentially a lightweight CNN, and it will watermark the audio. Okay, so in the lab, we will do zero shot, as we have discussed, only 10 seconds of reference, no fine tuning. And there are also different parameters you can set, such as the weighting. So classifier free guidance is also happen in the image. So classifier free guidance also, you can tune this kind of hyperparameter in image generation, not only in voice generation. And it controls how closely the output matches the reference speaker. So the lower the W, the more natural it sounds. Okay, so it can produce different language using the Llama 3 multiple encoder. So here to summarize again, we have the S3 tokenizer preserving the speaker's voice patterns. And finally, we have final part, which is try to watermark the audio with the CNN. So in the lab, the Python script will actually find the reference speaker. So if you want to clone your own voice, you have to record 10-second audio and rename it exactly as reference speaker for it to work. Okay, so, and you can choose what you are going to speak, and also what language. So this is the lab configurations, and it will produce different sorts of language and wave files in the HPC server. So if you have written something like it will clone your voice at once, and then it will output your version of speaking English, your version of speaking French, and your version of speaking Chinese and Malaysian. So, and then this would be the report of the chat box output, and you should be, if you pick this as your project, you should also submit the report as well. So the key takeaways from the voice cloning: the S3 tokenizer extract the speaker identities into discrete tokens. That's how the voice is actually kind of captured. And you use the Llama 3, treat it as a reference. So treat it as a style guidance. And you have again to decode the waveform into back into the voice. And of course, back into the voice part, and of course, you have another neural network for watermarking every output. So the voice will be kind of marked as AI, whether you have named it or not. And this kind of model is cross-lingual. So one English clip can provide around 23 plus language. So in your project, you can try out different languages as well. Another project idea that you can try is simply to stitch the machine of how you can hear and machine how machines speak. So if you stitch them together, you can make a voice control chatbot. So you can convert the speech to text, and then text to the chatbot, and text back into the voice. Of course, you can do this in your own voice as well. So you can make a chatbot that talks like you. So combining all the three parts, your project should look like you created a chatbot that sounds like you, but it actually may be connected to a, say, Gemini API or Grok API. For the lab and for the code, I only did the simple pipeline, which is converting, stitching the text to speech and speech to text together. But as you can all see, if you combine the three, it would be kind of a more complete project that you can do. Okay, so I think it is a good time for me to pause and actually run the code. Okay. So let's see. So in the Moodle, there is a code called week 7. And there is also a guide called the project and code guide. So the project and code guide essentially is guide you through your project. Of course, you can simply follow the guide and use this guide as your cornerstone of your project. So for each step, it's already include the lab, and of course in your project you can do either one. So you can pick one to actually work on it, or you can simply integrate all the steps together and call it a project. Okay. So in the code there are, I think, 6 files, which is the first one essentially extract the audio features. So how raw audio becomes a number and to the log number. And for the whisper, it used a faster whisper and to convert automatically speech into a speech into text. So the actual code will download from, the actual speech will be downloaded from the Whisper repo. And of course, a Roku will generate text to speech. And voice cloning, you can clone your voice. If you do not set the, if you do not give it the reference speaker, it will clone, it will find the speaker that is used in the audio fundamentals. Okay. And of course, there is a pipeline chaining models end to end. So these are the Python script, and also this would be the slur that you would submit to the HPC server. Notice that I've changed the .sh file to a slur file, and because if I change that to slur, you do not have the execution permission program, so you do not have to write like chmod plus and so on and so on. Okay. So these are some simple, very simple commands that you can use. So let me just try to follow the guide and execute them, and so that you would know how to move on in your project. Okay. So week 7. And then I will log into the server. So I will remove this one first. So to upload to this file into this server is very simple. You just drag the folder and put that import in. So now you have all the files in here. You can look inside it to see what is written in it, and you can click view or edit. So view would be this. Or edit, you can edit it. So let's try to run the first code. So as usual, you enter your own account. Of course, if you forget your own account, you can of course use this as the shell. So this is the web page shell, but I kind of prefer using this one. Okay. But it's exactly the same. Okay, so I have my terminal. For those of you, if you log in, maybe it still said it's 25, but I think I've already increased to 50 gigabytes. So I've heard some of you cannot run the code, and I've checked, and I think because this quota is already full. Okay, so now if I kind of navigate into the folder, I will see all the code. Okay, so navigate into the folder and okay, so log in as you would usually do. Uploading the file, you can using the UI. I recommend using the UI to upload. Okay, so the first command is to find the file and then run it with slurp. Okay, so let me try to see if it actually runs. So, okay, so it runs successfully. Okay, so if you, okay, so what I've just did is, so you do not have to do, repeat what I've just did, I just checked whether it actually runs. Okay. Okay, so it runs successfully, and I will kind of explain what I did here. So the first script will run the audio fundamentals Python. It will kind of generate the spectrogram. So it will use the audio file, generate this text, generate this, it will get this audio file. It will kind of using the torch audio transform, make it into a spectrogram for you to see. And of course, finally, it will output the log mild spectrogram. So what the whisper actually received as the input. Okay, so you should also see the mild stats in this folder. So if I now go back to the server and I refresh the server, I should see this audio, this milestat text, and this image. So if I click into the image, you should see week 7, chapter 1 signal audio as numbers, and you should see the raw waveform of the audio, the mild spectrogram, the log mild spectrogram. So this is the actual whisper input. So you will actually be putting this part of the image to the whisper. Okay, so I will just try to download the voice. Hopefully I can play it.
And so, my fellow Americans, ask not what your country can do for you.
Okay, so this is
ask
just
what
the
you can
audio
do for
download
your
from
country.
it. So it will input to the whisper for the transcription. If you do not change anything. Sorry, I mean, if you do not any change the voice calling part, it will use this voice to clone. So, if I recommend for your project you use your own voice, but this is the default voice. of course, you can still use the default voice for a project, but yeah, but I think it would be more interesting that you use your own voice. So we have so let's go back to the 00 batch. So and then you can run the whisper to do the transcription. So what the whisper log v3 will actually do, it will actually get the audio file, do the filtering as we have discussed, encoder, pass encoder, encoder, and then it will output the token. The configuration for your model you can take is the beam size and whether it is filtered or not. So the simple code is just, you can just run it like this one. Okay. So I submit the job. So after running this one, the expected result is you should see the whisper transcript. So you should see that, and so my fellows, okay, maybe you should change this one. Ask not what your country can do for you, but ask what you can do for your country, okay? So that means the audio actually transcript properly. So this is the second part of the code. For the text to speech, it will generate two kind of wave functions called TTS voice 1 and TTS voice 2. So let me just run this. So again, for the text to speech, it will do it will actually convert the text into phenome symbols, like Americans will be transformed to the source of phenome symbols, and it will pass through an acoustic model, phenomes with the voice style and then convert into the monospectrogram, and the vocal detect or encoder will actually transform the monospectrogram into raw waveforms. Okay, so I picked two of my favorite voices and as your references. Okay. So to run this is pretty simple. Just add batch and then submit the code. So let's try.
一定要做佢每期呢個界面揾唔到，未揾到。佢每期呢度做，一定要去呢個得。應該都唔做。哦，呢個要買。係都係呢個。應該佢做嘅聲控制係有前景。
Okay, so if it runs successfully, it will generate TTS voice 1, which you can download and listen to.
In this week's lecture, we learned that audio can be represented as a log mouse spectrum, a grid of numbers capturing frequency energy over time. This grid is the actual input to the whisper encoder, not the raw waveform.
Okay, so this is voice 1, which I think sounds much better than me. And you can download voice 2. So maybe in the future, if these pipelines.
The Coral verifies an important principle. A small, well-trained model can beat a large model at a specialized task. With only 82 million parameters, Kokoro achieves near human-level naturalness on English benchmarks while running faster than real time on CPU.
So these are the two voices. And for the other parts, so it requires you to change the reference speaker to a waveform. Okay, so I'll just run this. So this one will download a reference speaker and then clone the reference speaker. It will actually take longer than usual. I think it will take around 3 minutes. What it does is try to clone a reference speaker. So while it is running, let me just get back to this slide. Okay, so voice cloning, it will clone for a while, and it will download a reference speaker, or we just heard, speak decoder, and extract the compact speaker embedding, and then try to do the text-to-speech decoder, try to inject this embedding as a style, and then and the language ID to control which language to generate. So the language ID is EN, it will be generated, say, clone EN. Okay, so it's finished. So let's check the results. Okay, so in here you see clone EN wave. So you want to range. So let's hear the Chinese waves.
语音合成技术可以让计算机用任何人的声音说话，这在现在人工智能领域中非常重要。
So this voice is actually this man saying. So this is.
And so, my fellow Americans.
So it's actually clone this one voice. Of course, in the project, you should clone your voice. And this
Louis,
is
priez comprendre la parole. À partir de ce temps, ce milieu de audio réel.
so I don't speak French, so I do not know whether they speak correctly. English is the same. Okay, so I think you should try this. I plan to use for you to try this in lesson, but I think the time is up. I think you can try this at home and to clone your own voice. So in order to clone your own voice, you have to change. So where is my reference? This file. So you must record your own voice and convert it into a WAV format and rename it exactly as a reference speaker for you for this to work. So I think I did clone my voice. So I think I have to dismiss the class because I ran over time. But for I will be here for a while if you have any questions. Okay, thank you.
真係講明。